Hello, in this video we're going to go over 14 different integration techniques that help us solve a lot of different types of integration problems. The first method is what you're all familiar with, is called the U substitution. You use U substitution when you can break up your integrand into two parts. One part that is a function of u and the other part that is derivative of u. Oftentimes the way U substitution is taught is you take u equals a function of x, in this case I took it as sine inverse of x, and then you take derivative of both sides, so you get du equals 1 over root 1 minus x squared dx. Solve for dx by writing down the rest of it in terms of u, and you would get dx equals cosine u du. This is oftentimes not the best way of doing this. Instead, what I suggest is you evaluate x in terms of u first. So in this case you have u equals sine inverse of x. Evaluate x as sine of u, and then you differentiate. As you see, it is actually much better doing it that way. You get to dx equals cosine of u du much faster. Here are a couple of examples you can try. The next method to keep in mind is the denominator and radical substitutions. So this is an extension of U substitution. However, keep in mind that sometimes there may not be an obvious substitution, but it's always good to try denominator or radical substitution. For example, if you're given the integral of 1 over 1 plus root x raised to the power of 4, u equals 1 plus root x would be a very good substitution. Third thing to keep in mind is completing the square. So here is an example. X over x to the fourth plus 2x squared plus 2. Complete the square in the denominator, you would be able to solve the problem. Number 4, integration by parts. Surely this is a method that you are all familiar with, and the way it is taught is integral of u dv is equal to uv minus integral of v du. The way I would like to think about that is I would take my integrand, break it into two pieces. One piece is the u and the other piece is dv. So u is a piece that if you differentiate it becomes simpler, and dv is a part that you can easily, or at least relatively easily, integrate. So that's what you want to keep in mind. Here are a couple of examples. Natural log and tan inverse of x. Try these out. Anytime you're using integration by parts or U substitution or any other technique of integration, keep in mind that you might have to do it multiple times. You might have to do the method multiple times, and you might have to use different methods multiple times. For example, if you're integrating e to the power of x cosine of x, you will be able to evaluate this one if you don't give up. So you want to do the integration by parts twice in order to get the value of e to the power of x, integral of e to the power of x cosine of x. Next method is partial fractions. Whenever you're trying to evaluate integral of a rational function, you would want to use partial fractions. The very first thing you want to do is to divide the numerator by the denominator. Here's an example. Integral of x cubed plus x plus 1 over x squared plus 1. In order to evaluate that, do long division and then see what you end up getting. Next thing you want to do is you factor the denominator. If your denominator has simple real roots, then you would want to use partial fractions. Write down the fraction as the sum of ai over x minus bi, where bi's are the roots of the denominator. Here's an example you may want to work on. Next thing you want to do is, if you have real roots in the denominator but they are repeated, if you have a factor of x minus r to the power of n, then you want to use the sum of fractions with constants in the numerator and powers of x minus r in the denominator. And here's an example that you can work on. If you are given rational functions with non-real roots in the denominator, then for each factor ax squared plus bx plus c to the power of n, you would want to write down one fraction for each of the powers of ax squared plus bx plus c. So it would be ak plus bkx over kth power of ax squared plus bx plus c. And then you simplify that, you evaluate ak and bk, and then you go from there. Here's an example, 1 over x to the fourth plus 4 dx. And sometimes it may not be easy to factor the denominator. Next method of integration is what I call rationalizing substitutions. In this method, you would like to turn everything into rational functions. So if you have radicals, a substitution for radical would be really helpful. Next is trigonometric functions. When you're trying to integrate trigonometric functions, these are the things you want to keep in mind. If you are given an integral of the form cosine of x to the power of r times sine of x to the power of s, you have multiple scenarios. If r is odd, then you take u equals sine of x, because what you need to do is you can break up cosine of x to the power of r into one piece, which is cosine of x, and write down the rest of it in terms of sine. So you can write down the entire integrand in terms of sine and then multiply it by cosine. If s is odd, you do u equals cosine. You break up sine of x to the power of s into one copy of sine, write down the rest of it in terms of cosine, and then you'll be able to integrate. If both r and s are even, then you would use half angle formulas. Sine squared of x is equal to 1 minus cosine of 2x over 2, and cosine squared of x is 1 plus cosine of 2x over 2. If you are given integrals of the form tangent to a power and secant to another power, what you do is this. If r is odd, you would use u equals secant, derivative of u, which is secant times tangent, is present there. So you break up tangent to the r as tangent times an even power of tangent. Then you write down tangent squared as secant squared minus 1. Everything is going to be in terms of secant, and then you can use u equals secant of x. If s is even, you can write down everything in terms of tangent. Derivative of tangent is secant squared, and then you go from there. If both r is even and s is odd, then you would want to use integration by parts. So what you do is you write down powers of tangent in terms of secant. You get everything in terms of secant, and then you can use integration by parts. Here's an example, integral of secant cubed dx. If you are given functions of the form sine of ax times cosine of bx, what you need to do is you need to use product to sum formulas. And I have a video on that. I will put that right on the screen here so you can take a look at how you can use product to sum or complex numbers. Here's an example, integral of sine of x plus 1 times cosine of 2x. Rational functions of sine squared and cosine squared. To integrate these, we write down sine squared as tan squared over 1 plus tan squared, and cosine squared as 1 over 1 plus tan squared. And then we do a u substitution for tangent of x. And here's an example, tan squared over 1 plus 3 cosine squared of x. So we write down cosine squared as 1 over 1 plus tan squared, and now everything is in terms of tangent. Then you use u equals tangent of x, and everything becomes in terms of u. You get a rational function of u. If you have rational functions of sine of x and cosine of x, this becomes a little bit more tricky. So what you do is you use u equals tangent of x over 2. Sine of x becomes 2u over 1 plus u squared, and to get to that equality, you could use sine of x equals 2 sine of x over 2 cosine of x over 2, and then you can get to 2u over 1 plus u squared. And then you can substitute cosine of x by 1 minus u squared over 1 plus u squared. And here's an example. Number 11, trigonometric substitution. If you're dealing with integrands that are of the form square root of x squared plus a squared, then you would use x equals a tangent of u. If you're dealing with integrands that have square root of a squared minus x squared, you would use x equals a sine of u. And if your integrand involves square root of x squared minus a squared, you would use a equals secant of u. In each instance, you have to limit your u value in a way that your square root becomes easier to simplify. Here are a couple of examples of trigonometric substitutions. Number 12, using symmetry. This method is applied for definite integrals. If you are evaluating a definite integral of the form integral from negative a to a of f of x dx, as long as your function is odd, that integral would be 0. And here is an example. Next method is limit swapping. This method is something that I have some videos on. I'm going to leave some of the videos here for you to review. In this method, what we do is we do a u substitution in a way that it swaps the limits of integration from a to b and from b to a. And here is a famous example. Number 14, differentiating under the integral. Sometimes it is possible to take the integrand, write it down as a function of two variables, differentiate using this formula, and evaluate the integral. Here is an example which I will do a video on that, so you can watch that video and know how exactly this method is being used. And this brings me to the end of this video. If you like this video, make sure to subscribe to the channel where you can find more videos like this. And I will see you in one of the other videos.